You are looking at a vibration spectrum, and there they are. Every time we are seeing the peaks that are perfectly exact multiple of the fundamental frequency, or you can say 1x 2x 3x of the running speed. So most of us see and think, what are they? These are harmonics. I know everything about that, right? But the real question should be slightly different, that actually why they are. Okay, what is actually physically happening inside that machine to create them? Okay, that should be the real question. So because harmonics doesn't appear randomly, so they are kind of a direct fingerprint of the shape of the vibration signal. So we will understand that connection, and I believe that after watching this video you will never look a spectrum in the same way again. Okay, so let's start with the basics first. So the first thing that we are going to discuss is what is harmonics. Okay, so harmonic is a frequency at a whole number multiple of the fundamental, or you can say the exact multiple of the fundamental. Now you will say, what is this fundamental? So fundamental is the, of course, it's also known as 1x. Okay, and also, or you can say it's a kind of a shaft running speed. So everything else is the multiple of it. So let's assume, to make it more clear, let's assume that pump is running at the 1500 rpm. So if I will be converting this 1500 into hertz, how much it will be? Remember that how we learn in our last videos to convert rpm into hertz. Just divide rpm by 60. Okay, so you will be getting the hertz. So once you will divide 1500 by 60, you will be getting 25 hertz. Okay, so 1500 rpm, or you can also say 25 hertz. This will be your 1x. Okay, so, or you can say the first fundamental frequency. So if I will double it, what will happen? It will go to 50 hertz. That will be my 2x. Then what will be my 3x? 75 hertz, of course. Okay, but here is the most important thing that normally training skips over. That in a perfectly smooth machine, very perfectly smooth machine, we will only see 1x, only one peak, only and only one peak, zero distortion, nothing else. Okay, so now the question should come, that from where then now we are seeing these harmonics, the other frequencies, that 2x 3x 4x, from where these things are coming up. So that is the machine that tells us that there is some kind of a distortion in my signal. Okay, that is something is happening that is not allowing it to have a exact same sinusoidal. Okay, and this distortion actually live in where we will find it in the time waveform. So what is the source here? So the source is the time waveform. Now think of the time waveform as a raw truth, or you can say the actual motion of the machine plotted over the time. So the spectrum is what we get when we ask that what frequencies are hiding inside the signal. Okay, so time waveform is the actual motion, and definitely the spectrum will be helping us to identify those frequencies, or you can say the hiding frequencies, right? So the FFT, or you can say the fast Fourier transform, it will answer that question. How it will answer? By breaking the waveform into the individual frequency component. Okay, so FFT is the process that we will be taking the time waveform, and we will be, with the help of the FFT or fast Fourier transform, it will help us to convert it into the spectrum. Okay, so here is the rule that ties everything together, and surely I will be requesting you all to remember this, that the shape of the time waveform always determines that what you see in the spectrum. Okay, so let's say pure undistorted sine waveform, what you will see? Only and only one peak, that is 1x. Okay, no harmonics at all. And let's say if there is any kind of a distortion or distorted time waveform, definitely it will bring up me the extra peaks there. Okay, these are our harmonics. Okay, so now rest of this video is the rule that applied to the 5 real time waveform shapes. So we'll be discussing here 5 real time time waveform shapes here. So let's start with the first one, that is, let's say, the pure sinusoidal waveform. Okay, so the pure sine wave is definitely it's our baseline, smooth, perfectly repeating, and every cycle is identical to the last. So what you will see in the spectrum? One spike at the fundamental, nothing else. So in the field you will get close to this with unbalance, a clean dominant 1x minimal, right? Minimal. Very rare harmonics. Why I am saying here rare harmonics? Because we know that in the field nothing is smooth. Okay, nothing is exactly same. Okay, that's the reason that why you will be seeing with the minimal harmonics. Okay, or rest will be a very smooth sinusoidal waveform. So the machine is doing the same thing every revolution, so it's a smooth linear way, no hard contact, no impacts, nothing. I know most of you will argue that 1x is not only unbalanced. That we will be discussing in the future sections, than when we are going to discuss different faults. I know that this is just for example, right? So the next one, first one is the pure sinusoidal waveform that we have just discussed. The second one is the clipped one. Okay, so that means clipped means now something get into the way, some obstruction is there, some distortion is there. Clipped, okay, so a clearance run out, a component hits hard stop. You can see that you can think of that one component is trying to move up, but something came in between or something hit very hard to stop that movement, right? So the signal tries to reach its natural peak but gets clear cut from there. Okay, so this is known as the clipping. So how this clips actually determines exactly that which harmonic should appear. So normally what happen, there are two kinds of clipping. One is the symmetric clipping. So in this, what will happen, that both peaks are flattened equally. Okay, both sides it will be flattened equally, so it will always give you the odd harmonics. So in the spectrum you will be seeing 3x, 5x, 7x like this. And if there will be asymmetric clipping, that means one side is smooth, another side is only getting hit hard, right? So it will give you a odd harmonics, or you can say both, not odd only odd, it's even in odd both. It will give you 1x, 2x, 3x, 4x, 5x like this. So whenever you see in the spectrum 1x, 2x, 3x, 4x, 5 like this, that means one side is smooth, another side is hitting hard. Okay, and if you are seeing only and only odd harmonics, that means both sides something is obstructing. So lock that in, that equal clipping both sides, you will be getting odd only harmonics. And one side is clipped or one side only is smooth and other side is restricted, then you will be getting both even and odd, that is 1x, 2x, 3x. So that distinction is so important that it has its own dedicated video coming next, don't worry for that, right? So now the third one, what is the third one, is the square waveform. So square waveform is nothing, that it's the same like that we have discussed before. It's kind of it will always give you the odd harmonics. That means the clipping is so hard from both sides that it will make looks this time waveform as a square. The top will be almost flat and the bottom will also very much flat, so it looks like a kind of very hard hitted, or you can say the very hard restrictions are there both sides. Okay, it will make you see a square type of waveform, right? So in this case what we will see normally the same, that odd harmonics, 1x, 3x, 5x, 7x, 9x, odd harmonics only we are going to see, and amplitude definitely will be decreasing. 1x will be, let's say 5 mm, and then 2x will be maybe around 3 mm, and maybe 3x will be more less than that, and 4x will be, so amplitude will be reducing. 1x will be the maximum, then after that 3x, then 5x, so it will reduce slowly. Okay, so we will never see we will not see a perfect square waveform normally in the real identical machines, right? But when a waveform starts approaching, it becomes some kind of a rectangular shape. That is a serious finding. It will be a very rare case, something serious is happening. Other side is also very hard punches, machine is getting very hard punch, and downside also very hard punch. Okay, so very rarely you are going to see this, but we are going to see this. But anyhow, just to clear the all kind of waveforms, what kind of waveforms can be there. Okay, so the machine is spending a significant portion of the revolution hard against a mechanical limit. That means another side, one side also very hard restriction, and another side also very hard restriction. Okay, so now we will be discussing the fourth one, that is the asymmetric waveform. Okay, so asymmetric waveform means one side of the waveform looks very different from the other. The positive peaks are, let's say, at different heights, and the negative peaks are of the different heights. Okay, so that asymmetric produces both and even and odd harmonics. Okay, and the fault list that cause it read like a diagnostic graded sets, or you can say the angular misalignment, decentric rotor, bend shaft, directional looseness, lots of examples. That all this stuff we are going to clear it out in the next sessions that are going to come, when we will be starting in this series the all kind of faults, fault analysis. So the time waveform give it away first. If the two halves of each cycle doesn't match, let's say, that means the upper half is having different amplitude and the lower half is having different. Okay, or you can simply say that the upper half of the waveform is having a different shape and the lower half is different. Okay, so what normally such kind of waveform is known as the asymmetric, because it's not similar to both sides. Okay, so if you will be going and check the even harmonics, they will be there, of course, even as well as the odd also. Okay, so even harmonics is a spectrum are not noise. Okay, they are the information. The machine is telling you that one half of its rotation is different from the another half. That's it. Okay, that's why in the most of the looseness case you will be seeing 1x, 2x, 3x, 4x, 5x like this continuously, even and as well as the odd, because the movement is asymmetric. One side the things are going at different amplitude, and another side it's going at the different amplitude, right? And what is the last one? The last one is the impulse. What is this impulse waveform? Any kind of a very sharp spikes on a, okay, like let's say that each one, like each hit is followed by the any kind of a rapid ring down as the structure briefly resonates. Okay, then once the structure resonates, then silence, then resonate, then silence. Okay, so one peak, another peak, or you can say one spike, another followed by the another spike. Okay, so each spike is it's a kind of a impact. Okay, each spike is a impact, something hitting, or you can say something is touching with something, or something is hitting with something. Okay, repeating at the fault frequencies, right? So let's say that any bearing fault is there, rolling element bearing defect is there, gear tooth damage is there, or any kind of loose component is there that is again and again striking. Okay? So all will produce this kind of a spectrum, and in the time waveform you will be seeing a very sharp peaks, or you can say a very sharp spike. Okay, so in the spectrum normally these impulsive waveforms spread energy across a full wide frequency range though, so the spectrum look very very busy, and it's kind of elevated across the broad bands. Okay, so not concentrated at one or two peaks. So spectrum we will seeing a very much busy with the peaks. Okay, lots of peaks you will be seeing there. So this is exactly why the enveloping and demodulation techniques are there, it's exist, and they extract and amplify only the impulsive content to make the fault frequency visible. Okay, before it show up clearly in the standard spectrum. That's the reason in such case, if you will see the time waveform, it will give you comparatively more idea. Okay, if let's say very severe bearing defect is there, or something severe hitting is there, so you can very easily see the spikes in the time waveform. That's why in such cases time waveform are very important for the analysis. Okay, so the rule one more time. Okay, so every waveform shape we just covered, same rule every time. Okay, pure sinusoidal means one spike, symmetric clipping means odd harmonic. Okay, and let's say if you want to push it to the square wave, and that's odd harmonic, ladder gone longer, that means the restriction is too hard both the sides. Okay, and what is this asymmetric? That means one half is not matching to another half. Okay, the top half of the time waveform is not matching to the bottom half. What we'll getting here, even and odd, both harmonics will be together. That means 1x, 2x, 3x, 4x like this. And what is the impulsive? Impulsive, that means something is very hitting, something energy is spreading very wide, like one side it's resonating and another side is okay, so something is hitting. So the spectrum is what is the spectrum? Now spectrum is a translation of the waveform. Okay, just remember this line, it's very important. What is the spectrum? Spectrum is the translation of the waveform, and what procedure that we are using to convert time waveform into spectrum is known as the FFT, fast Fourier transform. Okay, so when that something unexpected appears in the spectrum, okay, don't just stare at the peaks. Okay, just go to the time waveform and look at the shape. So spectrums tells you what, waveforms tells you why. That's the reason in the vibration analysis we need both. Please remember this. Okay, spectrums tells you what and waveforms tells you why. Okay, so anyways, next video we will be covering up symmetric versus asymmetric clipping. Okay, we'll be deep diving inside that to make you guys more clear what is this symmetric and what is this asymmetric, and why this we are getting odd harmonics only and why we are getting even harmonics. Okay, so definitely we'll be also discussing some kind of specific machine faults that will be producing such kind of patterns. So if you ever wondered by why misalignment shows a strong 2x, that video can be the answer for that, right? So hit like if it helped, and subscribe so that you can catch the next one, and drop a comment what waveform type do you see mostly in the field. Okay, till there, take care of yourself and your family. Meet you again. Thank you. Bye.